The next speaker is PhD candidate and my soon-to-be colleague, Rocco Zerlotti. Rocco from Parma, Italy, has a master's degree in biomolecular chemistry from the University of Parma and is currently industrial Marie Curie PhD student at Nanion with academic affiliation at the University of Regensburg in Germany. So, Rocco, over to you.
Okay, thank you, Ceci, for the nice introduction. So, today I would like to talk to you about the functional characterization of the human GAT1 that I did mainly with the SURF-RAN1 technology, so the solid supported membrane-based electrophysiology. As a quick agenda of the talk, first of all, I would like to briefly introduce to you the technique, in case some of you don't know it, and also the target, so the human GAT1. Then I would like to briefly go to the sample validation. Then I would like to have a deep look into the GABA-induced current with the solid supported membrane electrophysiology. And in the end, just the functional characterization, so the Km and the GABA sodium stoichiometry. Okay, so about some basics on the technique. We have, as you can see here on the left, we have our gold sensor, and we functionalize the surface with an artificial bilayer that is composed by a thiol layer and a lipid layer on top. Then we let the sample that can be composed by native membrane fragments or proteoliposomes that are expressing the protein of interest, of course. And we let it adsorb on top of this artificial bilayer. And this generates a capacitive-coupled system. So basically what happens is that all the currents that we see are transient because once we charge the capacitor completely, the current stops flowing and so decays. Another important thing is that we don't have any kind of direct voltage control, so the measurement starts at 0 millivolt. So here, just a general workflow for the surfer. So we start with a non-activating, so we start perfusing a non-activating solution that doesn't contain the main substrate. And this is important because basically we get rid of the mechanical artifact that is generated by just the fluidics going into action. And we also get the baseline. This can also be used, though, to generate an ion gradient or a co-substrate gradient if this is needed. Then we perfuse the activating solution that contains our main substrate, and hopefully we activate and see a current going on. Generated. Then in the end, we restore the initial condition by perfusing again the non-activating solution. So we have basically the reverse transport reaction. Okay, just to stress on some basic key concept. Again, the current recordings happen at 0 millivolt. And the driving force is just a substrate gradient. No, so it's not voltage driven. All the currents are transient, and as you can see here, just some example, on the left are the currents that you can see on the SSME, and on the right are the same currents reconstructed as they should look like in a normal conventional patch clamp environment. So if we have a low transient, this is usually associated to the stationary transport current, and you should see something like this in a patch clamp environment. If we have a fast transient, that usually is associated with a pre-steady state current. Pre-steady state current is actually an out of equilibrium conformational rearrangement of the transporter. So we have basically charges that are crossing the electric field of the membrane, but not in a dynamic equilibrium as the transport is. Or we can have more complicated situation like the one that you can see below. So basically, we can have a combination of pre-steady state currents and transport currents. Again, some terminology, I guess everybody is, all of you know them very much, but EC50 is just the substrate concentration that is needed to reach half the maximal amplitude of a certain parameter. So it can be charge, or it can be the current, at peak current or current at a certain time point. or whatsoever. And Km is just a particular case of EC50 that is the Michaelis-Menten constant. Okay, just for the target itself, so the human GAT1. Human GAT1 is its main function is the reuptake of GABA from the synaptic cleft inside the presynaptic neuron. And to do that, it has to exploit the energy that comes from the inward-directed sodium gradient that is normally existing in nature. And so for the stoichiometry, we have that for each GABA molecule that is reuptaken, 2 sodium ions and 1 chloride ion are co-transported. So this is the most currently accepted. Actually, there are some debating about the number of sodium ions that can be reuptaken, and also if the chloride is actually always coupled in this way. The transport anyway is electrogenic, so that's very good, and we can use electrophysiology to characterize this protein. And also this is an important target in pharmacology because a lot of diseases are associated with dysregulation in GABA homeostasis. Okay, so moving on to the sample validation. Here what I just did is I had my vesicles, CHO vesicles overexpressing human GAT1, filled with potassium chloride. Then I perfuse with sodium chloride, so I generate the sodium gradient without activating transport. And then in the end, I perfuse with a solution containing the same amount of sodium chloride plus oversaturating GABA. So now I am activating the transport. So here on the right, you can see the results of this experiment conducted on CHO vesicles overexpressing human GAT1, and you can see I have this nice peak here. Then for control, I also used CHO vesicles empty, so not expressing the protein of interest. And of course, I mean, luckily, I didn't see any kind of current rising. And I also wanted to assess if actually the GABA, so if this transport was related to sodium and chloride as it should be. So I just perfused with GABA, but in absence of sodium and chloride. And again, I didn't see any current rising. Still, I wasn't happy, so I wanted to also check the functionality of the living cells. So I used the patch liner that we have in-house here. And since I felt very lucky, I just went straight for a dose response curve. I mean, a dose response experiment with different GABA concentrations. So I used the patch clamp technique. I performed it in the whole cell mode, and I kept the voltage hold at minus 70 millivolt, as usually is the neuron resting potential. And luckily, again, I was able to see these nice currents here. I did the Hill plot of the currents, and I found out this EC50 or Km of around 12 micromolar. That is very good agreement with the literature results. Okay, so now the tricky part. So I wanted to really dissect the currents that I could see in SSME. So here again, this is the same current we saw before. So basically high sodium gradient and then oversaturating GABA perfused. So I wanted to have a close look at the current, and what I could observe is that what I could see is two different rising phase that here, I don't know if you can notice them well, but there is one that is very fast and one is lower. And then again, for the decay, I have two different decay times. So one slower, very slow here, and one that was faster. So actually here, I asked myself some questions, because if the peak would represent the transport, as usually can happen with the surface-supported membrane electrophysiology, then I should not see all this kind of different rising time and decay time. So what I did was like, let's try and kill the sodium gradient and see what happens. So here I just filled up my vesicles with very high sodium chloride, and then I generate a very small sodium gradient because I had 135 millimolar sodium chloride inside, and then I perfuse outside with 150 millimolar, so the gradient is like just 15 millimolar sodium chloride. Then again, I activate with oversaturating GABA. And what you can see here is that now we lose the slow rising phase, and we have a very fast rising phase, followed by, again, a very slow decay phase through all the activating time. Again, I was not happy, because at this point I asked myself, where did the slow rising phase and the other decay phase end up? So I say probably that can be something that is related to the sodium gradient. So let's just go back, keep a high sodium gradient, and just lower GABA. Let's see what happens. This. So basically, I could see 3 different phases in the current. So one is the fast current that we could see in absence of sodium gradient, in nominal absence of sodium gradient. The second one basically has this decay time that is consistent with the first decay time I could observe, and again the third rising phase. So at this point, I wanted to check what all these peaks were about. So I just did a deconvolution of, and I tried to really dissect all these processes. I was able to do that, and here you can see just the deconvolution of the peaks. And I also tried to say what these peaks are individually. So the first peak actually is very similar to a process that has been observed in past clamp in literature. They actually managed to achieve a fast solution exchange by using photocage GABA and just using a pulse of light and free this GABA very quickly in the solution. And both rising time and rise and decay time of this peak are very consistent with the one that this guy found. And so basically, this should be either GAT1 occlusion or the full carrier flipping from the outward-facing conformation to the inward-facing conformation. Then the second peak is quite tricky. Still, I don't have an answer for that. So my ideas is that this could be either sodium release inside or a sodium leak. So there are also in literature many examples of channel-like behavior of transporters. So this could be it, since it's anyway something that is affected by sodium gradient. And in the end, the last phase, I thought it was transport. So now switching to the functional characterization, I studied this very slow decay phase. So here you just see 2 different ways of measuring this. So in the case of a very low sodium gradient, I was able to reconstruct the current as basically they could appear as a stationary transport current, and then just, of course, read the current amplitude. And in this case, I just read the current at a time point in which both processes, so the both pre-steady states that we saw before, were at 0. In both cases, I was able to obtain these Km values that are in very good agreement with literature results coming from 2 electrode voltage clamp measured at a voltage close to 0. So conditions that are, let's say, close to the one that we have on the surfer. Okay, lastly, I wanted to shed a bit of light on the sodium GABA stoichiometry. So here I will spare you the physics, but basically what happens is that the charge can be seen as a function of the ratio of the chemical potentials of sodium and GABA here. And most importantly, when the charge is 0, the delta G is 0. And so basically this ratio equals the ratio of the stoichiometric ratio of the 2 substrates. So here I just played around with the concentration in order to obtain specific chemical potential ratios. And as you can see here, at 0 charge, we have a 2 ratio stoichiometry between sodium and GABA. So at least for what I am able to see, sodium and GABA has a stoichiometry of 2:1, as is the most accepted in literature. So again, for a quick summary, SSME is a suitable technique for measuring currents on human GAT1. The currents, the GABA-induced current on human GAT1 show a very complex behavior because they are basically triphasic. And again, lastly, sodium and GABA stoichiometry appears to be confirmed as 2:1. So that is all, and thank you for the attention.
Thank you very much, Rocco. I think we have time for one question.
Have a question like more on the technical side.
Yep.
So basically, just to get a good idea of your technique, the dimensions, spatial and temporal. So the cells, there is no cell per se, but how close, like you can put, like the typical size of your vesicles, how intact are those vesicles, how close the electrodes. So first, let's go to do the spatial component.
Okay, so I don't know about this, the actual size of the vesicles. We know that we have on top of the gold surface, we can have access to millions of transporters. And the electrode is actually some millimeters.
Some millimeters
yeah,
away, because
yeah.
normally you would want them to, because conceptually this is like end plate potential, the same principle is just kind of on steroid with recent technical advances. Normally you want to be as close as possible, so I would expect something like 100 microns or less, preferentially much smaller.
I never measured the actual, but maybe.
And then related question would be like temporal resolution. The best timing you showed was like couple of milliseconds.
Yes.
But I wonder, because I'm not talking about resolution of electronics, obviously it can do microseconds and less. But because of the positioning of all the geometry, you would have a lot of stray capacitance and some delay. So how much that influences? Can you even go like below 1 millisecond with this setup?
So it depends on the sensor type. So if you go to with 3 millimeter sensors, then the time resolution, the maximum time resolution is about 30 milliseconds. But if you use 1 millimeter sensor, so you have a surface area that is actually smaller or the same size of the ion jet, then the maximum time resolution that you can achieve is 1 millisecond. Sorry, 3 milliseconds.
Okay, yeah. So you're basically on a millisecond time scale. So the best, the fastest, that was my impression, that maybe you are limited, because if these are sodium ion channel voltage gated sodium channels involved there, you would expect sub-millisecond rise time there.
Yes, and exactly like I could see the triphasic thing only with 1 millimeter sensor.
But
with 3 millimeter is impossible.
That trace specifically was that you are limited by your equipment actually there.
Yes, of course, it's the time resolution of the technique.
Yeah,
so you know about the electrode?
For the size of the vesicles, I did do DLS measurements, and they're usually 100 to 200 nanometers in small. Yeah, we usually prepare them ourselves, and we're doing tip sonication. So by that. No, we purify the membrane from cells, and then we reconstitute them into those vesicles by tip sonicating.
Yeah, but then you have transporters in those vesicles.
Yes.
So you have to make those transporters soon somehow. So I don't know. Okay, yeah. But that was like my other remark is that you said that it is at 0 millivolts, but since you have working transporters there, that's a 0 millivolts by preparation at like 0.0 in time. But once you have transporters going, they will create.
They will build voltage.
Yeah, so that will develop certain potential on the membrane. You may well be looking at 50 to 100 millivolts of potential across the membrane. Actually, you have no way to measure it, but with like transporters at high concentration in this membrane, they will develop gradient, salt gradient across. You would have difference in sodium definitely in your case.
Yes.
That will by itself like 60 millivolts easily or more of membrane potential in those small vesicles.
Yeah,
So they are not strictly 0 millivolts.
No. So the potential will build up during the
Mhm.
measurement, but
Yeah.
like
So
some several hundred milliseconds after the peak. Anyway,
definitely,
so basically at the beginning you don't have a significant voltage build-up.
Yes, I think we have to continue these discussions afterwards. Thank you very much for your contribution.